Alright, so let's look at a couple examples here on how to apply friction to dynamics problems. And as we'll see, it's nothing too crazy, so to speak. It's just one more step we have to do in problem solving. And pretty soon, hopefully, it'll become second nature. So here we have a problem in which a block that weighs 5 newtons, alright, it's held stationary against a vertical wall. Alright, so held stationary. Ooh, that's good. That means we're in equilibrium. We have an upward directed force of 6 newtons exerted on the book at an angle of 30 degrees above the horizontal. Alright, we'll call that our applied force. That's 6 newtons. The angle is 30 degrees. Coefficient of static friction between the wall and the block is 0.9. Calculate the magnitude of static friction force between the block and the wall. Alright, so I listed what I know, what I don't know, so let's draw now a diagram of what's going on. Rather than solely drawing a free body diagram, I'm actually going to draw the block and the force is acting on the block itself, just to kind of help visualize things a little bit more, right? Because we have a wall here. So a lot of times walls are depicted with like this kind of diagonal slash line just to signify that it's stationary, not really involved in the problem. Alright, so there's our block. It's held against the wall, so maybe if I draw a free body diagram, I'd have a dot here. So it's held against a wall because it has an upward directed 6 Newton force, 30 degrees above the horizontal. Alright, so that means upward, and based on how I pictured my diagram here, upward and rightward. And that's my applied force. Alright, where this angle here, that's angle theta, with respect to the horizontal. Let's see, what other forces do we have here? It looks like we've got force of gravity acting straight down. Alright, and then we also have friction. So looking at what direction the friction force will point, there's a couple of different ways we could reason it. One would be looking and seeing, okay, well, force of friction is going to act opposite the direction the object would move. Well, if this object would move, it would move straight down, so therefore force of friction has to be straight up. Alright. I also drew it a little smaller than force of gravity. I did that on purpose because my applied force is off at an angle kind of with respect to horizontal and vertical. We're going to have to break up the applied force into a rightward and upward vector. So force applied in the x and force applied in the y. Alright, so looking at this, since we want to solve for the force of oh, we have one more force, don't we? We have one more force going on. Right? We have a surface, therefore we have a normal force. Our normal force is acting to the left, perpendicular to the surface. There we go. I knew I was missing something. Alright. And I knew I was missing something because I looked at my diagram. I'm like, wait a second, this object's going to accelerate. It accelerates rightward, which it can't have because it's in equilibrium. Alright, so we want to solve for the force of static friction. So summing my forces vertically, I didn't set up a coordinate system. We'll call upward positive y, we'll call rightward positive x. So summing my forces, we're in equilibrium, so mass times acceleration is 0. We've got 2 upward forces, that's the force of static friction, what we're solving for, and the y component of my applied force. Alright, and we've got a negative force of gravity. Alright, so this tells us that the force of static friction is going to be equal to the weight minus, well, let's figure out the y component of the applied force. So that's going to be opposite my angle, so I choose the sine function. So I take my hypotenuse, here's my applied force, times the sine of our angle of 30 degrees. Not going to plug in the number yet, but it's a nice number to deal with. Now let's see, looking at this, we know the applied force, we know the weight, we know the angle. Oh, great. We can just solve. And then I'll want to talk about this problem one more moment. But we plug in 6 newtons minus, oh no, that's 5 newtons, excuse me. 5 newtons minus 6 newtons times the sine of 30 degrees, which is 1/2. Alright, so it's 5 minus 3, which gives us a value of 2 newtons for the force of static friction. Now I do want to mention, you might think, oh, well, we're dealing with friction, so we could have just used the expression that the force of friction is equal to mu times the normal force. Right, but be careful. For static friction, this is only the case for the maximum value for static friction. Alright, so we couldn't just use this expression because we don't know that this is the maximum value for the static friction value. It's just some value for static friction, may not be the maximum. And in fact, we can compute it to check to see if it's maximum, but I'm not going to spend the time doing that. Alright. Alright, so this next problem, I'm just going to talk through it, through some work that I have written here. The reason for that is just because I don't have time, frankly speaking. Anyway, so the question here says how to dump a filing cabinet. So we've got a 50 kilogram steel file cabinet in the back of a dump truck. The truck's bed is also made of steel and it's slowly tilted. What's the magnitude of static friction force on the cabinet when the bed is tilted at a 30-degree angle? At what angle will the filing cabinet begin to slide? There's some notes here on what the value of kinetic and static coefficients are. Alright, so listing what we know. Alright, looks like we know the mass of the filing cabinet. We know the angle at which it's tilted, so just looking at the first part I should say. We know the 2 coefficient values. So we're listing those out, and we want to solve for, at first, the force of static friction, and later on, the angle at which it slides. All right. So sketching out a diagram, we have a ramp problem. All right, so the bed of the picked-up truck is this ramp. And I'm using this square to represent the filing cabinet. Looking at the forces acting on our filing cabinet, we have gravity acting straight down. We've got normal force perpendicular to the surface. And then we have the force of static friction acting the opposite the direction the object would move. Right? So if there was no friction on this ramp, the filing cabinet would slide down the ramp. So therefore, force of friction has to act up the ramp to prevent that sliding. Right? So it acts along the surface, opposite direction of the motion, or the way the object would move. So looking at this free body diagram, this force diagram, I also set up a coordinate system and labeled some angles. So I'm calling positive x down the ramp and positive y perpendicular and upward from the ramp. And then I've got my angle theta. Based on this coordinate system, my force of gravity needs to be broken down into x and y components. So I did that with this triangle here. So all this part of this we've seen so far has been stuff we talked about before in problems. All right, so this right now, the filing cabinet has not slid yet. It's just sitting on the bed of the pickup truck. So therefore, it's in equilibrium. So if we sum our forces, the forces must sum to 0 because it's in equilibrium. So looking at my x direction, we only have 2 forces acting that way. We've got the force of static friction, and we have my x component of the gravitational force. All right, so since they sum to 0, those must be equal to each other. So we have the force of static friction, which is what we're trying to solve for, is equal to my x component of the gravitational force. All right, so that is looking at my triangle here. That's the opposite side, so we use the sine function. My hypotenuse is the force of gravity. That's also equal to mg. So my expression here becomes the force of static friction is mg sine theta. And luckily now it's all in terms of things we know, because I know mass, I know the acceleration due to gravity, and I know sine of 30 degrees. This all gives me a value of 250 newtons in the end. Now again, we could not just use the expression that the force of static friction is equal to mu times the normal force, because again, that's only valid for the maximum value of static friction, which we do not know if that's the case here. Now, what angle will the filing cabinet begin to slide? The second part of this question. In this situation now, so we're basically raising the angle of the bed of the truck up to the point of just when the the filing cabinet begins to slide. This is the moment where our force of static friction becomes its maximum. It's just when it turns to its kinetic value. So this is the type of language you're looking for when you know that you actually now you can use this formula. All right. So now we have a situation where we're dealing with maximum value of static friction. So looking at this expression, all right, this tells us we're taking mu times the normal force. Since we're dealing with static friction, it's our static coefficient value, and we're dealing with the normal force on the object. Now looking at our force diagram, again, since our object, well, not just that it's in equilibrium, but also if this were accelerating, it's not going to accelerate kind of off of the plane, so to speak, of the incline. So therefore, our normal force must equal the y component of the gravitational force. Sorry, my screen just kind of slid. All right, so the normal force must be equal to the y component of our gravitational force. So then looking at our right triangle that we've drawn, then our y component of the gravitational force is going to be the hypotenuse of our triangle times cosine of theta, since this leg is the adjacent leg of my triangle, with my angle being there in that corner. All right. All right, so in plugging it in, we are taking mu times the force of gravity times the cosine of theta, where force of gravity is just mg. So my expression ends up being mu mg cosine theta. All right, so that's great. So now we have one expression we found for the maximum force of static friction. All right. Now, just in the previous part, we found another expression for the force of static friction. All right. We actually need to find another expression because we're trying to solve for angle. And right now we have two unknowns, right? We don't know angle, and we also don't know the maximum value for static friction. All right. But in the previous part, we used summing the forces to find a second expression. Whoops. Sorry about that. I want to erase that and that. All right, so now we're solving a system of equations, right? But what's nice here is we don't have to rearrange anything like that. We can just set, this equal to this. All right, so in doing that, what we end up having is we have mu mg cosine theta is equal to mg sine theta. Mg cancels out, so the weight cancels from both sides, and we end up with static coefficient times cosine theta is equal to sine theta. So divide both sides by cosine, we have mu static is equal to sine divided by cosine of theta, which we actually have to combine, right? So we have mu static is equal to sine theta over cosine theta. Right now, this theta is in two different trig functions. We need to combine it into one. So this is where we use our knowledge of trig, realizing that sine divided by cosine gives us tangent, allows us to then make theta into just one term. All right. So then to solve for angle, we take tangent inverse of both sides. So we end up with tangent inverse of our coefficient of static friction, which was 0.8 given in the problem, which gives us an angle of 38.6. So this cabinet won't begin to slide until it reaches that angle. So I hope that gave you some better understanding on how you can apply your knowledge on how friction behaves and the formula for friction into your standard dynamics problems.